到点了，我已经关声音了。
Hi everyone. I was muted and I was trying to ask you if you can see my screen and no one answered. I forgot to turn on my mic.
Yes, we
So,
can see the screen now, sir.
yeah, okay. Okay, good. Uh, so this session, I'm going to talk about decision tree, one supervised machine learning algorithm. And the example that I'm gonna look at today is actually is a classification problem to classify if an image is cat or not cat. So the first section, decision tree. Here I'm going to talk about decision tree model and a structure. So let's say that we have this data table, class classification, cat classification example. As you can see, we have 10 training examples or 10 rows. And then we have 3 features, X1, X2, and X3. The first feature, X1, is ear shape, the face shape, and the whisker shape for the
No, 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 no.
third feature. And the last column, which is our target, shows that the image is cat, refers as 1, or not cat, 0. So if you take a look at this data table, it's a categorical or discrete values. For example, for the ear shape, the first feature, there is no numbers, right? There's no numerical value, right? They're categorical. For example, we have 2 categories for the ear shape, pointy and floppy. And for the second feature, face shape, we have another 2 possibilities, which is round or not round. And for the whisker presence or it is absent, right? So each feature has 2 possibilities. And then the last column, which is Y or the target, shows that the picture or the image is cat or not cat. Is cat means 1, not cat is 0. And this is our X, this first 3 columns as X, the features. So if you take a look at this figure here, this is the structure of the decision tree. So this figure on the top left shows the biological tree. Maybe this one is not look like, doesn't look like this biological tree, but anyway, the machine learning practitioners decided to actually say that it is like decision tree. Maybe it's like the upside down indoor plant, right? Which the first node is called the root node. If you take a look at here, this structure here, the first node is called the root node. And then if we go one level further downward, then the nodes, these ovals below the root node, are called decision nodes. And then the last rectangles or the last nodes here on the bottom of this decision tree, they're called leaf nodes. So a decision tree is made up of root node on the top, and then the decision nodes in between, and then the last nodes, which are called leaf nodes. And then if you take a look at this one, so the first node is filled out by ear shape. And then the decision nodes, you can see this, the left one and the left branch is allocated to face shape and the right one to the whisker. You remember that in our data table, we have 3 features: ear shape, face shape, whisker, and then we are gonna classify the image, which is cat or not cat, right? And as you can see, these 3 nodes are filled out by these features. The first one, ear shape, face shape, whiskers, and on the last nodes, you can see that the decision is made. So cat or not cat, cat or not cat. And you have 2 branches, right? The left branch and right branch. So let's say if you have an example, the image, this is cat, right? And then for this cat, the ear shape is pointy, as you can see in the picture, and the face shape is round. And then the whisker, you see the whisker present, right? They're present. This cat has whisker. So if we give this training example, this new set example, new test example to this decision tree. So here, So the ear shape, what is the ear shape of this cat? It's pointy, right? So if you start from root node, the ear shape is pointy. So we goes to the left or right because the ear shape is pointy. We choose this path. We go to the left branch because the ear shape is pointy, and we reach out this decision node here, the face shape. Now, what is the face shape of the cat? It says the face shape is round. So between not round and round, we choose this path, this sub branch, which is round, and then we reach out this node. And this node says that this image would be related to the cat. So your decision tree make a prediction and said that this image is for cat, which is correct, right? Because the image was for cat. Correct? But anyway, we have different structures for the architectures or pattern for decision tree, right? For example, instead of this decision tree, we can have something like this, ear shape, and then whisker, and then the leaf nodes, or this type of decision tree, right? Or this one, or this one. But which of them is correct? We should use one of them or all of them. Or for example, on the root node, for example, let's take a look at this decision tree architecture on the left, this one. So on the root node, why you chose ear shape, this feature? Why you didn't choose face shape? So these are the questions that when you want to build up a decision tree architecture, you should ask yourself. So which structure is good for this problem? And then the nodes, the root nodes and the decision nodes, what feature I should use for the root node and the decision nodes? What is the priorities? What kind of priorities I should follow to build up my decision tree? I can get a good prediction just by using one decision tree, or I need all the possibilities for the structure of the decision tree. I need maybe 10 decision tree structures and see that those 10 decision trees say about that classification, about that image, if it is cat or not cat. Maybe I need the opinion of all those decision trees, right? But later on, I'm going to show you that we usually get different or some decision trees, not just one, maybe 4 decision trees like this one's here. And for example, let's say this decision tree classify the image cat or not cat. How about this one? We take a look at the answer of this decision tree, and then this one, and then this one. And then we vote them, right? We get the vote from all of them and see what is the majority of the vote. Maybe 3 of them, 3 of these 4 decision trees say that the image is cat, and just one decision tree, for example, this one, says that it is not cat. So we say, okay, from 4 votes, 3 of them say that 3 of the decision trees say that it is cat, and just one of them says it's not cat. So our decision would be the image is cat, right? So we vote on them and see that what is the vote, right? So learning process. What is the learning process of a decision tree? How it works? You remember that we had 10 training examples, right? You have 10 pictures of dogs and cats, right? So let's start from the first node, which is the root node. And let's say that we choose ear shape for the root node. Why ear shape? Why not face shape or whisker? We're going to talk about it in the following slide. But for now, let's say that for the root node, the first node, we choose ear shape. And then we take a look at these 10 training examples, and we know that the ear shape has two possibilities, pointy and floppy. And go through these pictures and see which one has floppy ears and which one has pointy ears. And then we split these training examples, these 10 data points, we split them on this feature, on ear shape. And then let's say that we can see that 5 of them, they have pointy ears. We put them here. And then five animals of these 10 animals, they have floppy ears. And then we put this 5 on the right branch, right? For example, let's ignore the right branch and let's focus on the left branch with these 5 animals, right? So after ear shape, the pointy one was this 5. And then let's say the next decision node is the face shape. And then we see that from this 5 animals, which of them has round face and which of them has not round shape. So if you take a look at here, you see that 4 of them has round ears, round face. This one has a round face, 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 but this one here doesn't have a round face, right? So we put 4 of them on the round, this sub-branch, the round face, and 1 of them, this one, on the not round face. And as you can see here, on this sub-branch, all of them are cat. And on this sub-branch, all of them is dog. Now it's time to make a decision. We don't need to go further to the next level to split on another features, because right now my subset of data, they're pure. What do I mean by saying pure or purity? This is 100% purity. It means that 100% of this sub-branch is cat, and 100% of this sub-branch is dog, completely dog, or this one completely cat. It means it is 100% pure, and then we can make a good decision. We can make a good prediction, right? So right now, these nodes are decision nodes because we can make a prediction, we can make a decision and classify the animals into cat or not cat. And then the same process on the right branch. These are the floppy ear shaped animals. And then in the next step, we might focus on the whisker, which of them has, for example, whiskers, which of them doesn't have whisker, and then go to the last stage and make a prediction and classify these animals into dogs and cats, right? This is how decision tree works. And this is the one, for example, this is the decision tree. It starts from root node, the ear shape, which has 2 possibilities, pointy, floppy. The left branch is this decision node, face shape, which has 2 possibilities, round face shape, not round face shape, and then make a decision, cat or not cat. On the right branch, the floppy ear shape. In the next step, we come to this decision node, whiskers. Whiskers has 2 possibilities. We can split the subset of data on this feature, the whisker, present or absent, and then this decision node result in these 2 leaf nodes, which decide the image is cat or not cat. This is how decision tree works. But there are some There are some questions that you need to ask yourself when you're building up a decision tree. The first one, how to choose what feature to split on at each node. You remember, for example, for the first node, why I used ear shape. I could use face shape. Another one might come and say that I want to use whisker on the root node, right? There are different opinions, so there are different possibilities. But which one is correct? For example, if one of the feature is the cat DNA, we don't have this feature here, but let's say that the cat DNA is a feature that I'm gonna split the data on this feature. And we know that DNA is something that is very accurate. If you have DNA of something or an animal or a human being, for sure, 100% you can say that this animal is dog or cat, right? So if I have a feature on this root node, then I can split the data points on this accurate and pure feature, and then I have two subset of data, left branch and right branch. You can see that on the left branch, 5 animals out of 5 is cat. And this one, none of them are cat, all of them are dogs. So this feature is very pure. And then if we have such features, we should put this feature on the root node and start our decision tree with that pure features, right? As you can see, because DNA is very accurate feature, and at the first stage, at the earliest stage, it can classify your data points very well and correctly and put the dogs and cats in the separate categories, and you can make a decision if you have the cat DNA. But most of the time, it's not like that. The features are not that much pure or accurate. So, for example, let's say this is a root node. Let's start with the ear shape and see and measure the purity. So we are trying to maximize the purity or minimize the impurity. And right now you know that what I mean by saying purity, right? Purity means that our splitting on a feature has the maximum improvement, and the data can be classified in a nice way. For example, if we start splitting the data on this feature ear shape, then we have two possibilities, pointy and floppy. On the left branch, you can see among 5 animals, 4 of them are cat, right? 4 of them is cat. It means 4 over 5. And on the right branch, from 5 cats, just 1 of them is cat. And the rest of it, the majority of it, is dog. How about the face shape? If you start from face shape on the root node. And then you can see on the left branch for the round face shape, out of 7 animals, 4 of them is cat. And on the right branch, from 3 animals, 1 of them is cat. The rest of them is not cat. For the whisker, on the left branch, 3 over 4. On the right branch, 2 over 6. By this measurement, we can say that which of them, ear shape, face shape, and whiskers, they deserve to start the splitting based on them, right? Which one deserves to be on the root node, on the starting point, right? But I'm gonna tell you shortly that how these fractions can help us to decide which features should be used in the root node at a starting point. But before that, the second question that you should ask yourself is, when do you stop splitting? So, for example, this is a root node of a decision tree, right? and then you split on this feature. There are two possibilities, left branch and right branch. And then from root node, which we refer depth 0 or level 0 to the root node. And if you jump or if you make one steps downward and come to this level, it is depth 1 or level 1, which is one level below the root node. And then if you go further downward, you reach out depth 2 or level 2. If you need one more steps, because for example, at this level or at this depth 2, you still cannot make a decision or classify the image if the image is cat or not cat. You need to make another steps and go to depth 3 or level 3, right? But when you should stop, when you can realize that, for example, I should stop my decision tree depths at depth 2, because you cannot go to the infinity. You cannot make your decision too large. When your decision tree is too large, you are actually you're exposed to the risk of overfitting. So by keeping your decision tree small enough, you can reduce the risk of overfitting, right? So somewhere you need to stop. But what is that point? When you can decide to stop your decision tree and not go one level further downward. First of all, when a node is 100% one class, it means when you obtained purity, the maximum purity. You remember the cat DNA? You see, the cat DNA is a very accurate feature, and it can classify, it can say that each picture is for cat or dog. And then by splitting the data points on this feature, the cat DNA, then at the earliest stage, you can have these two classes. The left classes, all of them are cats. The right classes, all of them are dogs. This is the maximum purity, right? And then you don't need to go further because you've already classified your data points into cats and dogs. 100% cats, 100% dogs. This is the maximum purity. This is 100% pure, and you don't need to go one level further. So now you stop your decision tree. Second, when splitting a node will result in the tree exceeding a maximum depth. For example, when you're using the decision tree, you can predefine the number of depth that you need. For example, you set that I need my decision tree to have just 3 level, or I need it to stop at depth 3. And if this is the case, this decision tree stops at that level and it doesn't go further. The third one, when improvement in purity score are below a threshold. For example, after some levels, after some depth, so for example here, you get these two classes. The left classes shows that from 7 animals, it predicts that 4 of them is cat. On the right branch, from 3 animals, just 1 of them is cat. And the rest of them, the majority of them is dog. Maybe someone says that this is a good accuracy. Maybe out of 7 animals, I could classify 4 of them as cat. And here on the right branch, from 3 animals, 1 of them is cat and 2 of them is dog. Maybe this accuracy is enough for me. And maybe if I go further, one level further, this accuracy might not change that much, right? For example, maybe out of 7, again, I have classified 4 of them as cat. I have this fraction. Or this fraction might increase a little bit to 5/7. And this one stays the same. So because by going one level further downward to another decision node doesn't improve my decision or prediction that much, I stop my decision tree at this level. The fourth one, when number of examples in a node is below a threshold. For example, on this branch, you see that we have just 3 animals. Let's say at first you have 1,000 animals, and right now, at this point, you have just 3 animals. And it is below, for example, you say that after I get 10 animals, maybe I need to stop the decision tree. Right now, you have just 3 animals. Most of them are in the left class. So you need that. I think it's enough, because right now I classify these 7 out of 10 on the left, and just 3 of them, uh, 3 of them are on the right branch for this class, in this class. I think this is enough, because right now I can make a good decision with acceptable accuracy that which one is which. This is dog or cat, right? Maybe that's enough. You don't need to go one level further. So these are the questions that you should ask yourself to stop the decision tree and not go one level further to make your decision tree too much large, to put your decision tree prone to the risk of overfitting. But how you can measure the purity? Remember that you need to measure the purity, and then you can fill out the root node and the decision nodes. Because at first, when you're going to build up your decision tree structure, you need to choose a feature first and split the data point on that feature. But which one deserve to be on the top of the decision tree, and we start the splitting based on that feature. Which of them should be in the root node? And the solution is measuring the purity. How we can measure the purity? Entropy. Entropy as a measure of impurity. So if you have these 5 animals as your data set, which 3 of them is cat and 3 of them are dogs, right? So this P1 shows the fraction of examples that are cats. So 3 out of 6 are cat, 3/6. This is P1. And then you can use, if you take a look at this figure, the horizontal axis is related to P1, and the vertical axis is related to H of P1. H of P1 shows the entropy. And we use this graph, this parabolic graph, to represent the entropy, the H of P1. And for example, 3/6 is 0.5, right? Is 1/2, 0.5. So if you take a look at this figure, this parabolic figure, you see that 0.5 for P1 is here, which is correspond to this point where the entropy is 1. So when P1 is 0.5, or when you're from your data set, you have 50% is allocated to cat and 50% to dog or another class, then P1 is 0.5. And this is the worst case scenario where the entropy is 1. When entropy is 1, it means the purity is the worst, right? How you can increase your purity? By decreasing the entropy. For example, when P1 is 1, it means all the animals are cat. Then P1 is 1, 6/6. 6 animals are cat out, right? So then the P1 is 1, and then you see that 1 correspond to entropy 0. Or all the animals are dogs, not cat. So 0/6. P1 is 0. When P1 is 0, it corresponds to entropy equal to 0. So it means when this group, all the animals in this group are cat or dogs, then the entropy is 0. It means it's 100% pure, right? Because all of them are just one kind of animal. There is no impurity. But if it is 50-50, it means the entropy is worse. It's a mixture of cat and dog. Half of them are cat, half of them are dog, and then the entropy is the worst. It's 1. Entropy changes from 0 to 1. You see, H of P1 changes from 0 up to 1. In this way, you can measure the impurity by calculating the H of P1, which is the entropy. And we know that entropy is not a good thing. We need to reduce it to make our subset of data more pure, right? And then you see that, for example, which feature can generate the smaller entropy. And then you start splitting the data points on that feature. If the other feature generates larger entropy, then you actually ignore it for now because it increases the impurity, right? So anyway, let's take a look at this figure, these examples. The first one, so we have 6 animals and neither of them is cat. It means 0/6. So P1 is 0, and we know that when P1 is 0, the entropy is 0. It means it's really good. It's very impure. When entropy is 0, very small, equal to 0, it means we are good. We are in a good shape because all the animals in this group are just one type, dogs. How about this one? Two of them is cat. 2/6. 2/6 is 0.5. Sorry, 1/3 is somewhere here, right? And then the entropy is like this much, 0.92. For the third case, 3 of them is 50-50. 3/6, 0.5. When P1 is 0.5, we have the worst case scenario. The entropy is 1. Is the worst case, 50-51. And then how about this case? You see that we have 5 cats out of 6 animals, 5/6. So 5/6 is somewhere here, which is correspond to this entropy, 0.65. And then in the last case, all of them are cats, 6/6. P1 is 1. P1 is 1, this point, which is correspond to entropy equal to 0. Right? So the first one and the last one are the best because they're completely pure because entropy is 0. The middle one is the worst case where the entropy has its maximum value, 1. How about these two? Which of them is more pure? This case or this case? Which of them is more pure? This one is more pure, right? This is better than this one. Why? Because the entropy 0.65 is smaller than 0.92. So this case is more pure. You can see that 5 animals are cat out of 6, but this one, just 2 of them, 2 out of 6 is cat. So obviously this one is more pure compared to this one. And there's a general expression for entropy. So you're familiar with this figure, and P1 we know that is a fraction of examples that are cat. And then P0 is equal to 1 minus P1. When P1 is the fraction of examples that are cats, P0 is gonna be the fraction of examples that are not cats, which is 1 minus P1, right? And then the general expression for calculating the H of P1, the entropy, would be this expression. If you rewrite it by replacing P0 to 1 minus P1, you get this final expression. If you calculate the P1, then you can calculate the entropy of P1 by using this equation here. And one note that you should consider, when you for one case, if you get 0 times log of 0, you should consider it as 0. Log of 0 is undefined in mathematics, but anyway, for the sake of simplicity and run the program, if 0 times log of 0, if you have this term, you should consider it as 0. So far, when you're building your decision tree, you need to choose which feature use for root node to start splitting the data on that feature, right? How you can choose that feature with more purity, to generate more purity, you measure the entropy, the H of P1, then you can decide which feature you can start the splitting on. And here we have some examples, 3 examples, and we want to generate and calculate the H of P1, the entropy, and then calculate the information gain. Information gain means the reduction of entropy. So because entropy is not a good thing, and we need to decrease the entropy from one level to the other level, right? You see the you see that the decision tree has different levels, right? We start from the first level, go to the second level, to the third level, up to the last level, which we have the leaf nodes, or this leaf nodes that you make a prediction, right? The good thing is, the good decision tree is that when you start from root node and you want to make one level further downward, then the impurity or the entropy should be reduced. This is called the information gain, right? For example, take a look at this first example. We don't know to split the data on ear shape, face shape, or whiskers, right? To choose one, you need to calculate the entropy and then obtain the information gain, how much the entropy could be reduced. Then you can decide which feature You can decide, choose one among these three features as a starting point on a root node or the others nodes, right? For example, let's take a look at this one. Ear shape, two possibilities, pointy and floppy, and you have 10 animals. And then this feature classify these 10 animals into two branches, two sub-branches. The left one, 5 animals. The right branch, 5 animals. But if you take a look at the left branch, you see that 4 of them, 4 out of 5 is cat, 4 over 5. P1 is 0.8. How about this one, the right branch? Just one of them is cat. So one from among 5 animals, just one of them is cat. So 1 over 5. P1 for this branch is 0.2. And then you have this equation to calculate when you have P1, then you can calculate H of P1 or the entropy using this equation, right? So we have P1, you calculate H of P1 for the left branch. Then for the right branch, you have P1, you already have the P1, you calculate the H of P1 or the entropy, 0.72, 0.72. For the next example, 4 over 7, P1, and then you calculate H of P1. And then for the right branch, 1 over 3, 1 cat out of 3 animals, and then calculate the H of P1, 0.99, 0.92, right? How about this one? For the whisker. So on the left branch, 3 cats out of 4 animals, 3 over 4, P1, and then calculate H of P1, 0.81. For the right branch, 2 cats out of 6 animals, 2 over 6, and then calculate H of P1, 0.92. But you need, if you see that for each example, for example, for this one, you have 2 numbers. For example, this one, both of them are equal. For the left branch and right branch, you calculate the entropy. For the second example, you have 1 entropy for the left branch, entropy for the right branch. This example, the entropy for the left branch and right branch. But how you can decide that which one is better, which one is more pure? There's one way that you can mix them together. For example, for this example, you have 2 entropy. You need to mix them together. For example, H of 0.8, the first entropy, with this coefficient. What is this coefficient or fraction? You see, at first, you have 10 animals. How many of these 10 animals exist in the left branch? 1, 2, 3, 4, 5. 5 over 10. Plus the second entropy, and its coefficient is going to be, you have 10 animals in total. And then how many of these 10 animals exist in the right branch? 1, 2, 3, 4, 5. 5 over 10. So this is the next step. The same thing for this one. You put this, for this summation, you need these 2 entropy. This entropy, you put it here. Its coefficient is going to be, at first, you have 10 animals. How many of them exist in their left branch? 1, 2, 3, 4, 5, 6, 7. 7 over 10. Plus this entropy here, and its coefficient would be the number of animals on the right branch, 1, 2, 3, 3 over 10. The same thing for the last example. And you need one more steps to calculate the information gain. To obtain the information gain, you subtract this parenthesis by the entropy of the root node, where we have the mixture of 50-50 cat and dog, 0.5. The same thing for this one. We subtract this parentheses that we just made in the previous slide by h of 0.5. The same thing for this one. And we know that on the root node, we have 50-50, 50% cat, 50% dog. So P1 is 5 over 10, 0.5, and h of 0.5, h of this P1 is 1, which is this one. So this h of 0.5 is 1, 1, 1. And then this parenthesis subtracted by 1 gives us this information gain. For this example, this parenthesis subtracted by 1 gives us this information gain. The same thing for the last example. So you see that information gain for us is important, right? And we are looking for a larger information gain. Larger information gain, that means that we can reduce the entropy better, right? So we take a look at the information gain. Which one has, from these 3 examples, which one has the larger information gain? 0.12, 0.03, 0.28. So this one is larger. So it means that this feature, ear shape, is a good option, is the best option for us to start splitting the data on.
进了吧，已经。
And then here is the general expression how you can calculate the information gain. H of P1 on the root node, which here was H of 0.5, minus this parenthesis. And you know that this parenthesis, how it is made, right? To entropy with their coefficients, right? For example, if this is the case, so P1 on the root is 5 over 10, 0.5. So P1 root is 0.5, H of 0.5 minus, on the right branch, you have one P1 left, and W left is the weight. You know how to calculate the weight, right? Weights are these fractions, this coefficient here, here, or here. I told you how to calculate them, right? So this is the W for the left branch, this is the W for the right branch, and this is the general expression. You have everything. You can replace these parameters with their values and then calculate the information gain. This is what we calculated here for 3 examples. And then we choose the larger information gain and its corresponding feature. And we start splitting on this feature, not face shape or whisker. So putting it together, we start with all examples at the root node, calculate information gain for all possible features, and pick the one with the highest information gain. This is what I just said. A split data set according to selected features and create left and right branches of the tree. You know about it, right? Keep repeating a splitting process until a stopping criteria is met. You know the stopping criteria. You know when to stop your decision tree. I talked about it in the previous slide. When a node is 100% one class, when a splitting a node will result in the tree exceeding the maximum depth, information gain from additional splits is less than threshold, or when number of examples in a node is below a threshold. Just a few animals exist, so I think it's time to leave the decision tree with those number of depth. And then here is that how this decision tree works. I talked about it, but let's repeat it again. So we have 10 data set, 10 animals. We start from, let's say, ear shape, because ear shape generate more information gain. And then we split the data on ear shape, and ear shape has two possibilities, pointy and floppy. And here the animals are split on ear shape into the left branch and right branch, 5 of them in the left branch, 5 of them in the right branch. And for at first, we ignore the right branch and we just focus on the left branch. We work on the left branch to make a decision that it's cat or not cat. And then we start working on the right branch. So for now, we cover the right branch and we work on the left branch. After ear shape, we got these 5 animals. Now it's time to split these 5 animals on another feature, let's say face shape, which has 2 possibilities, round, not round. Let's say for round and not round, we got these 2 classes, just 1 dog here on the right branch and 4 cats here. And then because 4 cats out of 4 animals, now we can make a decision. And here you see that the decision tree decided to this classes to be cat because 4 of them is cat. And then this one, you can see from one animal, it is just one animal and it is dog. So you can, for sure, you can say that it is not cat. You can make a decision. After working on the left branch, now it's time to uncover the right branch here and work on this one. So for the floppy ear shape, we have 5 animals. And for this node, we use another features, the last one, whisker. Whisker has 2 possibilities, present. Whisker is present or not present, absent. And by splitting the data, these 5 animals on whisker, we have these 2 classes, one on the left branch and one on the right branch. And you can see that this one is cat, so we can make a decision and classify the left branch as cat. And you can see on the right branch, all of them are dogs. So it's 100% pure of one type. So you can make a decision and put not cat here. So in this way, you can make a decision, cat, not cat, for the right branch and for the left branch. And for the right branch, you have these 2, cat and not cat. In this way, you classify. At first, you had 10 animals. You had 10 animals that you don't know they actually should exist in which classes, cat or not cat. So right now, at the end of the decision tree, you see that all animals exist in their own classes. For example, these are cat, this is not cat, this one is cat, this is not cat. We have 2 categories or 2 classes, right? We expect to have just 2 categories, cat, not cat. Class 1, class 2. And in this way, you classify 10 animals and put them in the class that they belong to, right? In section 4 of this lecture, I'm going to talk about using one-hot encoding of categorical feature. What does one-hot encoding means? So let's say that you remember this data table, right? The ear shape, face shape, and whiskers, 3 columns are the features, and the last column is the target, which is 1 or 0, cat or not cat. But in our example so far, for each feature, we had just 2 possibilities. For example, for the whisker, we had present or absent, 2 possibilities. For the face shape, round or not round or not round, just 2 possibilities. But let's say for this new example, for ear shape, the first feature, we have more than 2 possibilities. Pointy, oval, and floppy. We have 3 possibilities. So when it is 3 possibilities, it means that this node, this decision node, should be split in 3 sub-branches, right? Pointy, floppy, and oval. What's there's a solution, we call it one hot encoding, that we keep this target column here. We keep these two features, the second and third column, we keep it here. And then instead of the first column, which has 3 possibilities, we can make 3 new columns from each possibilities of the ear shape. So we have pointy, oval, and floppy, 3 possibilities. So we created 3 new columns: pointy ears, oval, floppy ears, and oval ears, right? Instead of this one, we changed it into 3 new columns based on its possibilities: pointy, oval, and floppy, pointy, oval, and floppy. And how we can fill it out? So for example, for the first one, the ear shape was pointy. So pointy ears, we allocate 1 to this one and 0 to floppy and oval because it is pointy. For this one, the second row, the ear shape is oval. So pointy ears 0, 0, and we allocate 1 to oval column or feature. The same thing for the rest of the training examples, and we get these 0 and 1 columns, right? And so far, we have 3 columns with numbers and 2 columns, face shape and whiskers, which are categorical, right? The possibilities are round or not round. They're categorical value, right? They're not numbers. So if a categorical feature can take on k values, create k binary features, 0 or 1 value. It means, what this sentence means, this means the task that we just did. We changed this column because it has more categorical features, 3 values, pointy, oval, and floppy. And then we created k binary features, or 3 binary features, 1, 2, 3. And they're binary. Binary means 0 and 1. 0 and 1. And in the next step, we can also change the categorical value of this column and this column to 0 and 1, because they have 2 possibilities. For example, for the face shape, we have 2 possibilities: round, not round. Let's allocate 1 to round and allocate 0 to not round. And then we can just change the categorical value to the numerical value. The same thing for the whiskers. And then this is the final data point, data table that we have, all in numbers. So this is one hot encoding. Why one hot encoding? For example, here, we said that if it's pointy, we change it to these 3 columns. So when it is pointy, so this column is 1, and we allocate 0 to this one and this one. It means that one of these 3 new columns are more important compared to two of them, right? For example, for the first training example, this column, which has 1, value 1, is more important compared to this column and this column, which has the value of 0. For the second training example, this column with 1 value is more important than this one and this one, which has 0 values. For all the training examples, you see that this one is more important. For this one is more important, this column, because the rest of the columns are 0. So for each training example, just one of them is more important and has the value of 1. Just one of them has the value of 1. For this training example, just one of them. For this one, just one of them. The other 2 columns are 0. For this training example, this row, just one of them is 1. These 2 are 0. For this one of them is 1. These 2 are 0. So for each training example, just one of them is important. That's why we call it one hot encoding. One of them is more important with a value of 1. And then I told you that how we can change the entire data table from categorical value into numerical value. And then it's easier to work on numbers rather than the categorical values. There's another thing. Let's say that okay, we have let's get back to our first data table with ear shape, 2 possibilities, face shape, 2 possibilities, whiskers, 2 possibilities. We want to add another feature like weight in pounds, which is number, and it is a continuous numbers, right? And then the target columns, which is 0 and 1, cat or not cat. So how you want to split the data point on a continuous numerical value. For example, when we wanted to split the data on whiskers, then we had 2 branches, present or absent. If we wanted to split the data on face shape, we had 2 branches, round, not round. For this one, 2 branches, pointy, floppy. But how about for the weight? How you want to split the data on weight? So there are some continuous numbers. How you want to create your sub-branches? So for this one, you need to define a threshold. For example, this is this data table, this weight. We want to plot the cat and not cat, this column against this column. Cat or not cat against the weight. The weight changes from I think 7.2 up to 20, right? 7.2 up to 20, the weight. So we have these data points. So you can define that, let's say that this is my threshold, 8 pounds, and whatever less than 8 pounds, I can allocate to one sub-branch, and whatever more than 8 pounds, this is the 8 pounds, right? Whatever on the left-hand side is one sub-branch, whatever on the right-hand side can be another sub-branch. But how do you know that this 8 is a good option, is a good choice for being a threshold? Why not 9, for example? Let's say 9. 9 is here, this green bar here. And then whatever on the left-hand side of this green bar is one branch. The rest of the data points on the left-hand side of this green bar is another branch, right? For example, when it is 9, yes means that less than 9, which are these 4 points for data, and larger than 9 means the right-hand side of this green bar, 9. We have 1, 2, 3, 4, 5, 6 data points. 1, 2, 3, 4, 5, 6 data. How about, for example, 13? The threshold, instead of 8 or 9, let's say it's 13 here. And then you have some data on the left for the left branch. We have some data on the left-hand side of this 13 on the right branch. But which of them is correct? You can have different choice, 8, 9, 13, the same way. That's what we did for choosing a feature, calculating the information gain. We calculate the information gain for 8. We calculate the information gain when the threshold is 9. We calculate the information gain when the threshold is 13. And then we compare the information gain of these 3 thresholds, these 3 choices, and we choose the one with the highest information gain, which is this one, which is related to green bar or 9 pounds. And then 9 pounds is my threshold, and then I can split the data on weight when the threshold is 9. All the data point which is less than 9 goes to the left branch, whatever data points or animals which their weights are more than 9 goes to the right branch. In this way, you can split the data points on that weight, which has continuous numerical values, right? Tree ensembles. What does tree ensembles means? You remember that I told you that just using one decision tree doesn't work that much well. We need ensemble of tree, or we need group of trees to see their votes and then get the majority of votes to make a decision. We cannot just trust on one decision tree. So the tree ensembles mean that we have a collection or group of trees. We have, for example, 10 trees, 20 trees, and we see that each tree's decision. For example, if you have 10 trees, ensemble of or group of 10 trees, then you have 10 votes, you have 10 decision. You take a look at them. For example, from 10 decision tree, 8 of them say that the image is cat, and 2 of them, they say the image is dog. So you say, okay, majority of them say the image is cat, so my final decision is cat. So you vote on them. So this is tree ensemble using multiple decision tree. These are highly sensitive to small changes of the data. Trees are highly sensitive to the small changes of data, so we need to have tree ensemble or group of them, because we cannot just trust on one tree, because it is very sensitive. If just a data points changes a little bit, then it impacts the decision tree's decision, right? So we need to have group of decision trees and get the majority of the vote to make a decision. For example, here, we're going to split this 10 data points on ear shape, and then we have 2 possibilities, pointy and floppy, and then we have these 2 branches, 2 classes. But if we just change this cat with pointy ears to this cat with floppy ears, and the rest of the animals are the same, then the information gained to tell us that instead of ear shape, you should start with whisker. You should split the data on whiskers, not the ear shape. And then your left branch and right branch are different. So you see, just by changing the data set a little bit, just the ear shape from pointy to floppy, the architecture of your decision tree changed from ear shape to the whiskers, right? So that's why we need the tree ensembles, a group of decision tree. For example, here, for this image, to decide that this image, to classify this image as cat or not cat, we have 3 decision trees. This one, because this image, the ear shape is pointy, the face shape is not round, the whiskers is present. So for decision tree, whiskers is present. So we choose this path, the left branch, because the whiskers is present for this cat. And we comes to this decision node, ear shape. So ear shape is pointy. So we choose this pointy sub branch, and then the decision is cat. So prediction is cat. For this one, the same thing. We choose a right path based on this information. And this tree says it's not a cat. But this one, the third one, it predicts cat. So 2 of them say that this image is cat. Just 1 of them says it's not a cat. What is the final prediction? Cat. Because the majority of the prediction says that this image is cat. Sampling with replacement. So what is sampling with replacement? Imagine that you have 4 tokens, red, yellow, green, and blue. And then you put these 4 tokens in the black bags that you don't see inside the bags. And then you put your hands into the bag and shake it a little bit and choose and pick 1 token, right? You take it off the bag and see. Let's say this is the first sample, right? You put all these 4 colorful tokens inside the bag, right? And then for the first sampling, you pick one. So let's say the first one is green. And then sampling, this is the sampling with replacement. So you need to put this green token that you just take it off, put back to the bag, and then choose another one. For example, the second one is yellow. And then you put this yellow token back to the bag, and then choose and pick another token. Let's say the third pick is blue. And then you put back this blue token inside the bag and pick another one. The fourth one is blue. So this is your sampling. The first one was green, the second one was yellow, and then the third and fourth one are blue, right? It is called with replacement because after picking 1 token, you need to put it back to the bag and then pick another one. You should repeat it 4 times. This is the first sampling with replacement. The second sampling would be something like that: red, yellow, red, green. The third sampling would be green, green, yellow, blue, red. And the last one, red, blue, yellow, green. This is sampling with replacement. We can do the same things with these 10 animals, these 10 data points. Let's say we put these 10 animals inside the bags. So you cannot, in reality, in real world, you cannot put the animals or pets in the bag because it is inhumane, right? But let's say this is a virtual bag, and then you put these pets, these 10 animals, inside the virtual bag like this, and then you can pick one for sampling, and then put it back into the bag and pick another one, right? For example, for the first sampling, you put 10 animals in this virtual bag and then pick one. Let's say this is the one with pointy ear shape, face shape, and whiskers present, right? And then put it back into the bag, into this virtual bag, and pick another one. The second one is this animal with floppy ear shape, not round face shape, and whiskers absent, which is a dog, right? And then put it back into this virtual bag and pick another one, this one. And you see, because you put them back after picking, you might have some cases that are repeated. For example, this one repeated here, this one repeated here. It doesn't matter, that's okay. So this is called the sampling with replacement to get this data table, right? And then from this sampling with replacement, the machine learning practitioners introduced the random forest algorithm to generate a tree sample. So this is how it works. Given training set of size M, for example, our training set was 10 animals. So the size of 10, and then you follow this for loop. For small b from 1 to capital B, use sampling with replacement to create a new training set of size M and train a decision tree on the new data set. So in this way, you can create 10 data table, right? You see here, I just mentioned that how we can create this table by putting all these 10 animals or 100 animals or 1,000 animals inside this virtual bag and pick one, put it back to the virtual bag, pick another one to create the second rows, the third rows, up to the 10th rows, the total number of animals. And this is the one data table. And then you can build up a decision tree and train your decision tree based on this data table. For the second decision tree, you can create another data table using this virtual bag and these animals in this virtual bag and sampling with replacement. You create second data table like this, and then use the second decision tree and train it on the second data table up to capital B number cases, right? And capital B can be 10, can be, I don't know, 50, right? And then, for example, you have the first data table, which is created using the sampling with replacement, and you have a decision tree, you can make a decision. You can create another data table using sampling with replacement and train another decision tree. And in this way, you can create a capital B number of decision trees, and then you can vote on them. The key idea is that even with this sampling with replacement procedure, sometimes you end up with always using the same split at the root node and very similar splits near the root nodes. It means random forest is good, but sometimes, for example, you created 10 decision trees, but most of them are very similar to each other. So if this is the case, you cannot make a very good prediction. But random forest is one of the best algorithm that people use it. But this is actually this is not a random forest algorithm. So we can do such things, but most of them are similar to each other. But random forest solve this problem, right? We created 10 data table with 10 decision trees following this for loop, but maybe most of them are very similar to each other and give us the same prediction. To addressing this issue, we introduced, the machine learning practitioners introduced the random forest algorithm, and they said there's a solution to differentiate the decision trees and make them to being different from each other. And the solution is randomizing the feature choice. At each node, when choosing a feature to use to split, if n features are available, pick a random subset of k less than n features and allow the algorithm to only choose from that subset of feature. What does it mean? It means that if you have, for example, we had, in our example, we had 3 features. But let's say if we have 10 features, okay, and choosing one optimum feature among 10 options is hard, right? So instead of focusing on 10 features, let's take a subset of these 10 features. So instead of choosing a best feature among 10 options, let's decrease it to 4 options and focus on these 4 features, and choose the best one to start splitting on that best option, right? And usually the k, for example, is the square root of n. So if you have, for example, let's say you have 16 features, right? The number of features is 16. Then get the square root of 16, and k is 4. It means instead of taking a look at the 16 features, and pick the best feature to split on, you just focus on K features, which is 4. So you just focus on 4 features and pick a best feature that you can split your data on. This is how random forest works to make a prediction. The other one, the XGBoost classifier, is another ensemble tree, the tree ensemble, which is more efficient and faster compared to random forest and the other decision trees algorithm. So the only difference between boosted tree, this boosted tree or XGBoost compared to the random forest, you remember this rule from random forest, right? We have a training set of size M, then we follow this for loop, small b equal to 1 to the capital B, and then we use a sampling with replacement to create a new training set of size M, and then train a decision tree on the new data set. But here there is a small difference here that we added to create the XGBoost. It is after using the sampling with replacement and creating new data, instead of picking from all examples with equal to 1 over m probabilities, make it more likely to pick misclassified examples from previously trained trees. So it means that, for example, here, you use the sampling with replacement from 10 animals, and you created this data table. And then you have a decision tree that you trained your decision tree on this data table and get a result. So some of them, because this decision tree is not the best, it cannot classify perfectly, 100% correct. So this decision tree, because this is the first one, it has some misclassified output. For example, the image is dog, but it classified, this decision tree classified it as cat. The second one is cat, it classified as cat, correct. But the third one, it was cat, but this decision tree classified it as dog. So there are some misclassified output. In the second step, the XGBoost uses those misclassified examples from previous trained trees to create the new data table. And then it trained the second decision tree on the new data table. So this is the difference between XGBoost and the random forest. It uses the misclassified examples to create the new and second and third or fourth data tables to train the next decision trees on, right? This is how it can correct itself and make a better decision. This is called the XGBoost, which is, again, a tree ensemble. The XGBoost, or extreme gradient boosting, is open source implementation of boosted trees, fast, efficient implementation, good choice of default splitting criteria and criteria for when to stop splitting, built-in regularization to prevent overfitting. This is one of the most important features that XGBoost has, the built-in regularization to prevent overfitting issue, right? And then high competitive algorithm for machine learning competitions, especially on Kaggle competitions. And then XGBoost can be used for classification and regression model purposes. For example, if you want to use it for classification, you can call the XGBoost package and import XGB classifier, and then you can get this model and fit your model on the training examples, and then make a prediction. Or if you want to use the XGBoost for the regression purpose, you can call XGBoost package, import the XGB regressor, as your model and fit your model on the training examples and make a prediction, right? So this XGBoost method can be used for classification and regression problems at the same time. And then when to use decision trees versus neural network. So for example, for classification or regression purposes, when you choose decision trees, when you choose neural networks, you can maybe, for most of them, you can choose either of them, but which one is the best? So let's take a look at the advantages or pros and cons of the decision trees and then the neural network, and then we can make a better decision to choose which of them. So decision tree work well on tabular or structured data, right? No recommended for unstructured data like image, audio, and text. It is fast. The small decision trees may be human interpretable. Neural network work well on all types of data. It's not like decision tree that is just work well on tabular, structured data. It works well, the neural network works well on all types of data, including tabular, structured, and unstructured data. Maybe slower than a decision tree. Works with transfer learning. Transfer learning means that you can use a pre-trained model, that the model is trained on a huge amount of data, and then the model is almost ready, and then you can train your model on the new data that you have and use it. And then when building a system of multiple models working together, if you want to building a machine learning system of multiple models to work together, it might be easier to string together multiple neural network compared to the multiple decision tree. So these are some pros and cons of decision tree and neural network, that it depends on the structure of your data and your problem and your output. You need to choose one of them. So this session was about the decision tree. I hope you got kind of familiar with decision tree, the tree ensembles, how it works and how it operates, the pros and cons. Yeah, that was the decision tree lecture. So do you have any questions? And I'm gonna upload, I think, 1 or 2 assignments. So some assignments, because next session is our last session, right? On November 25th. And then next session on December 2nd, we have a final exam, right? I think the project, we don't have something like project, but I want to just give you extra example instead of the project. It's kind of like project, but it doesn't matter, just a name, project, assignment, whatever. For the last assignments, I don't know, it's 2 or 3 assignments. I want to give you enough time to do that. So maybe 1 week or 2 weeks or 3 weeks after the final exam, you have time to complete and upload the last assignments or the last project. I want to put the last assignments, maybe 2, 3 assignments, in a package called project. And then you have enough time to do that, to do and upload that project, maybe 2 weeks after the final exam. So don't worry, just focus on the final exam, and yeah, on December 2nd, we have final exam. Please focus on the final exam, study hard, and don't worry about the final project. I'm gonna give you enough time to do that, even after the final exam. So if you don't have any questions, we can call it a session, and have a great day. Any questions?